that I'm going to do it with OLS, right? That's ordinary least square. So first I'll tell you which is my PRF. My PRF is yi is equal to alpha plus beta xi plus ui. My SRF is yi alpha cap plus beta cap xi plus ui cap, where yi cap is alpha cap plus beta cap xi. Now my problem, oh it worked, then I write slow. Okay, I'll write slow then. The problem is to minimize alpha cap comma beta cap summation ui cap square is equal to summation yi minus alpha cap minus beta cap xi whole square. Right, this is my current scenario. So my first order conditions are I think this is how it will go to summation minus from there yi alpha beta xi equal to 0. That would mean I think this will be n alpha, yeah. This, now if I divide this whole thing by n, this will also become, so this is my first normal equation. Now I'll go to the second point of my thing, which is du by cap square du beta cap. This will become minus 2 summation yi minus alpha cap minus beta xi into xi is equal to 0. That would mean summation xi yi equal to alpha cap summation xi plus beta cap summation xi square. Right, that will be my first normal equation. Wait, I'm looking for something. Wait for a second, stay with me. Yeah, so right with this, yeah. Now what will I do is I'll take this to be my second equation. Now using Kramer's rule, will I calculate beta cap, which will go something like n just xi. This is not gonna work, right? I don't even know what I've drawn so much that it's so angry with me. This Canva thing is not so good if you're thinking yourself of trying to teach on this app. While I'm teaching for myself, so it doesn't matter so much. So yeah, this makes my equation to be n summation xi yi minus I think this is it. Now I can also write this as this, since my this is y1x. Right, so this would be my OLS by this estimation. Now wait, let's go to new page. Yeah, so I'll start with new thing. Now what my intention would be here, now that I know a lot of things, I will do one more case, which will be yi equal to alpha plus beta xi plus ui subject to alpha is equal to 0. That is, I'm basically trying to estimate a model which is this. Okay, now the width has somehow increased. The width has not increased, so wait, let me reduce the width. Okay, now yeah, now what is my corresponding Lagrange here is, because it's subject to restriction, I will do it with the method of Lagrangian, is minimize alpha cap beta cap summation ui square. Right, this is what I will measure. This is minimize yi alpha beta xi whole square subject to alpha is equal to 0. Now I'll write my Lagrange. My Lagrange will be minimizing still alpha beta, right, summation yi alpha beta xi square minus lambda alpha this. Now this is very important every time. Now first order conditions, won't go so long, this one's quite quick. dl by d alpha equal to minus 2 yi minus alpha cap beta I xi minus lambda is equal to 0, because see this is there, so which is how it will become, right? It will become something. Wait, I'll not make it anything right now. Wait, I'll go to second condition. Wait, this we all know, this is how this goes. Yeah, so this is how it will go, and then we will go to this. Finally, now this is my third, this was my second. You always number them first, that's me playing with things. Use 3 in 1 or in 2 actually, that'll be a lot quicker So now I know this equation I'm going to use, which would be, I can use it here only. So this will basically become, this was my equation, right? This I've taken now to be 0. Now my beta basically becomes in this case. Now the difference here is that this is used from raw variables and not from the ones that we were using earlier. Yeah, wait. Let me erase something to at least complete this. Xi, yi. Wait, again, let me erase this. You don't know the kind of problems that I have. So instead of this, I'm using this now. Now, what I'm going to do here is, I'm going to delete this page. And I'm going to delete this page. So now a new limit on things. And we have recorded everything previous, so we don't care so much so. Now, where we have reached is now a linear model we have derived, and we have an estimated regression line. What I'm going to do is understand the interpretation of this thing. You remember you used to have a line in your 11th standard which was this. This is the equation of a line, where this is my intercept, this is my value of slope. So this will be my value of slope. Similarly, beta here is my value of slope. In case you didn't get it, we take this equation, we differentiate it with respect to x. Alpha will become 0, beta dxi will become 1, so my beta will become dyxi dxi, right? Now where can be used? If there's some cases where for instance we are trying to get price elasticity. So there we can use this, which would be np dy by dx x upon y. If my here y would be my quantity demanded, x would be my price, right? So my np would also can be written as beta xy. So this would be my some sort of interpretation of this. Right, now moving ahead to a log linear model. In a log linear model, a model would be somewhat of this kind actually. Wait, I think I did it wrong. Wait. Yes, yi alpha xi beta evi. Now if I take linear log on both sides, it will become this ln alpha plus beta ln xi plus vi. Now here if I differentiate this with respect to x, it would be Right, so this will somehow become a little like, did I not take cap? It was meant to be a cap. Yeah. This differentiation will become 0. Right, this will become this. It can also be written in the same form that we just wrote initially if I had to. Not that that's required, but just in case. And that's my elasticity again. Now I'm not going to prove the Gauss-Markov theorem fully. I'm just going to discuss it. So stay with me. When we say Gauss-Markov, we mean linear. We mean unbiased. And we mean efficient or minimum variance. I might make a video on that later, but not right now. Oh wait, well, okay, this is pointless. So yeah, this will be my thing. Now linearity would mean if my model is still the same, linearity would mean beta is a linear function. For instance, if I prove this, so what does mean? Beta is a linear function of y. Unbiasedness means estimate of beta cap is true beta. And third would be that it has minimum variance than any other estimator. So that's my OLS or best linear class estimator. Now I will go to something that is more currently of a useful value, which would be this conclusions. So this would be my quick conclusions if I have to. Beta is summation xi y upon summation xi square. Alpha is y bar minus beta bar x bar. R square xy is beta I. Right, this is yx, right? So yeah. Right, now summation uy square is 1 minus r square summation yi square, and this is variance of u is this upon this. Thus my standard error for if I have to calculate for beta would be right, and my standard error for alpha would be, so you can calculate everything, it's just that I am choosing not to right now. See, yes. Now let's do this. Now error variance. Yes, this would be my error variance. I'll just calculate it. No, I'll not. Wait, actually, this would be a bad idea. A very bad idea. Wait. You know my error variances. That is it. There's no discussion that's happening here. Or you can also write this as okay. So this is specifically for a two variable model. Now I'll do one more thing, which is coefficient of determination, which is what I'm looking for in life also. Coefficient for determination. Right. So this will go something like UI. Wait. No. So you know we have done R square, right? We have done this. Now similarly, now we have RSS. So not RSS. Wait, this is not. I'm confusing things. Wait, it's night and it can be. It was never meant to be just information delivery. So now coefficient of determination, it gives us what is explained variation over total variation, which is explained variation over total variation. What would that mean is this is my explained variation, this is my total variation. This can be written as ESS over TSS. Now this is explained sum of squares, TSS is total sum of squares, right? This is my R square, this is my ESS over TSS. Now another way of writing this would be 1 minus RSS over TSS, because ultimately total sum of squares is equal to ESS plus RSS. So I can write this. Wait, I'll show you. Total sum of squares equal estimated plus residual sum of squares. Now I can write this as I'm trying to ESS on TSS minus RSS. Dividing this thing by TSS would give me TSS by TSS minus RSS by TSS, which would mean ultimately 1 minus RSS by TSS, which is why this would be my thing, right? Which is why I can also write this as 1 minus summation UI cap square summation y square, which is how. Okay, so now what you do know or may know or should know is, for a two variable model, R square xy equal to R square xy. So what I can from here I can derive is r square xy is equal to 1 minus summation ui summation yi square, which will basically become my operation to be summation ui square summation yi square 1 minus r square summation ui square is equal to 1 minus r square summation yi square. So this is what I wrote a little earlier before, I think not on this page. Oh, on this page. So this is where I wrote this. So this is how it came. So clarity on this is there. I could prove a lot more things, I'm choosing not to, so pardon me. Next would be, let me show you one more thing, would be, so there are, you know this, right? We just discussed. This is summation. Now in this there are two cases, which is in which one is known and one is unknown, right? So when it's known we use z test to test it, when it's unknown we use t test, right? So now what to use is, I'll only do for beta, and I'm choosing not to wait, so be too bad. Yes, I'm joking. Wait, there's still two. Yeah, I'm choosing to do this only for beta and not for alpha right now, so don't expect that to be the conclusion. Now for beta we apply, firstly we'll apply z test and then we'll do this. So h naught is, wait, h naught is, yeah, beta is equal to beta naught, h1 is, h naught is not true. Okay, oh yeah, I figured. This is my this. Now under h naught, first case would be, I'll do simultaneous. In this is known, in this is unknown, right? So here my under h naught scenario would be z is equal to beta minus beta naught upon standard error of beta cap. Here would be t is equal to beta minus beta naught standard error of beta naught. Now you know this is my scenario here. Right, so this will become basically, wait, sorry, I did a blunder here, wait, yeah, wait, yeah, so wait, standard error of beta was this is what I'll write. Right, it's quite, yeah, so it's quite a hassle right now. So this will become something of the sort. Here also you had to write this, I did not write this. Now this has come. What basically becomes is, here you can write, if you want to, this can be calculated as right. This would be my testing procedure here, because here it's known so it will be quicker. Here it's unknown so we'll use t distribution and we'll use estimated thing, right? Now also, yeah, so there's no cap in this one. The cap is, I don't know, I think there's no cap in this one. There's a cap, so this will be like that. Now for both of them we will define critical region, which will be my W naught, which will be for 1, it will go something like Z, wait, Z greater than Z alpha by 2, right? And for another one it will be something like T greater than T alpha by 2 and minus 2, right? And decision rule will be except H naught if reject H naught. Similarly, for the other test it would go like except H naught if yeah, this is except only. Reject H naught if so this will be my thing. Now after that we can go to, I think we should go to another topic, which would be yeah, which would go something like with still what, yeah, so which will go like analysis of variance. By the term it's very clear, which would mean ANOVA, right? ANOVA. Now here my pen has become a stumbling piece of joke again, so let's do this. No, that would be 12, yeah. So this would be my ANOVA analysis. What is the purpose is? Purpose is test significance of ESS, that is estimated sum of squares. Right. Now, how will you do that? You will do that using F test. Right. Okay, so I think we'll just do this. So this is my source of variation. I'll make an ANOVA table right now. First of all, source of variation, sum of squares, degrees of freedom, mean squares, and F. So first is explained. Sum of square here will be summation xi square. Degrees of freedom is 1. This is my ESS buddy. This will be also beta. Wait, this is not coming out good. Wait, I need thinner pen. Wait, let's start. Again, this is for revision, my personal revision. Oh, that's why. Oh fuck, okay, wait, what have I done? This was, then I don't know, wait, it should be 10 then. This would be beta. This is my estimated sum of squares. Degrees of freedom is 1 here. This is my mean sum of squares, right? Then this was my residual. Residual is summation ui square n minus 2. This would be my mean sum of residual. F would be my MSC by MSR, 2 degrees of freedom, 1 minus n by 2. We also write total. Total would be summation y square and n minus 1. So this is my that. So this makes my F to be beta square summation xi square upon summation ui cap square upon n minus 2 square. So you can write this to be, because it's mean, right? So mean would be this. So this is my that, which with n minus 2 beta cap summation xi square beta square summation ui square. Now one ultimate result that you must note down from it is equal to t square, and this is how we can test the estimation. Now all we'll go to is multilinear regression model. For that, first let me delete this page, otherwise I might run out of something. Wait, yeah, so this would be my multiple regression. Now multiple regression model, if you take for instance a model like this, Now what is this? This is a multiple regression model. This would be beta 1, beta 2, beta 3, right? And this would be 1 x2i x3i plus ui, right? Now here what is beta 1 gives the average effect of, wait, I'll write what is effect. Beta 2 measures net effect of yi on x2i on yi, holding all other variables constant. That is holding any effect that x3i may have on yi, or x1i may have, oh sorry, not x1, but like, yeah. So this holding every other effect constant. So it does not give you the gross effect, it gives you net effect, right? Beta 1 gives net mean effect of all variables excluded from this model. Now the OLS estimators for this model will basically come from this problem. Problem goes something like, this would be my problem. Now how to solve this problem will be another thing. So this would be my first order conditions. I'll use them to solve. Now first order condition would be, firstly this would mean for second one it would mean, this would be my first normal equation. It's quite a thing, isn't it? I mean, if you will solve this, it will come something like this only. There's very little chance that it might deviate from this thing. So I don't think that should be a. Similarly, you can derive the third equation, which will be basically differentiating this from this. So you can similarly do the for the third equation. Now solving these will bring me my actual estimators of beta 2, which is summation x2i yi summation x3i whole square x2i x3i x3i yi, then summation x2i square summation x3i square minus summation x2i x3i whole square. The more you solve problems, the more this will sit in your mind as it is. Summation x3i yi summation x2i square x2i x3i x2i yi upon summation x2i whole square summation x3i square minus summation x3i whole square. Now we have done the estimators, we know this, that will come to later. Okay, yeah, I'll stop today at this point.